Okay, good afternoon. My name is Suraj Rampier, and today we're going to be going through Data Science 8 Fall 2016 Midterm. So let's go ahead and get started. So let's dive right into question number one, where we were presented with a graphic from the Daily Cal a couple years ago. And the question is asking, what is one of the important choices made by the graphic designers that makes it difficult to visually compare the numbers of crimes in various categories? So, what was that choice, and why does it make it difficult to compare values? Right. So right away, we can see that the numbers in this category and in this category and this category and this category, they're not really centralized around any one given mean, and they're all kind of spread out all over the place. Right. So here we have a 2, here you have a 63, but clearly this bar for 63 is not more than 31 times taller than this bar. Similarly, this bar has represents 23 robberies, and this bar represents 63 liquor law arrests, but this bar is taller than this bar, implying that 23 is greater than 63. Right, and we can say the same thing about 9 and 15 here. The bar for 9 hate crimes is taller than the bar for 15 sex crimes, which doesn't really make sense. So the important choice they made important choice not using a consistent scale across categories. Difficult because you can't compare values that are on different scales. So that was a pretty straightforward question. Not really a curveball there. And part B asks, hey, what if we have this table assigned to some variable crime in Python? What's a line of Python code that we could use to kind of fix this issue and create a visualization that makes a little more sense and that doesn't have the issues that this one had? Right. So typically we're used to, in our IPython code, having the function bar h, which would create a bar graph for us, and we know that bar graphs, they have a consistent vertical scale. So we can go ahead and use this thought process, or use this idea to create a graphic that kind of makes sense for us. So we can go ahead and say crime dot bar h, and so now we need to pass in the parameter that we want to be the x value for the bar graph, right, which is quite clearly year in this scenario, right, because we have years on the x-axis here, right, 2013, 14, 15. And what this will do, will create a bar graph that has a consistent vertical scale, which will make it easy for us, to compare numbers that are in different categories, where the magnitude of a number, or the magnitude of the height of a bar, will correspond to the number of values that are actually represented by that bar, which is what we're used to in a bar graph. So yeah, that's part 1B. Number 2, the table colors is created as follows: table.widthColumn, and then we make an array of blue, green, red, and purple. And now, so this question is asking us to find a numerical expression for the chance that all entries of colors.sample3.column0 are all the same. So essentially what it's telling us is, find the probability that if we randomly sample 3 times from this array, we're going to get blue, 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 or green, 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 or red, 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 or purple, purple, purple. That's what this question is asking us, right? Because we're sampling 3 times from this array, and we're taking column 0, which will be the results. So one way we can look at this is break it down into 4 cases, right? So first case would be that we get all blues. Our second case could be that we get all green. Our third case could be all red. And our fourth case, all purple. Right? So now we're going to have to combine both the multiplication rule that we talked about in lecture and the addition rule. But for each of the individual cases, we only really need to look at the multiplication rule. So right off the bat, what's the probability you pick one random color and that it's blue? Well, that's just a quarter. Now, what's the probability that the second color we pick is blue, given that the first one is already blue? Well, these are independent events, right? Randomly picking another color has nothing to do with the color that we are already picked, if that kind of makes sense, right? So our probability is, again, 1/4, because the outcome of this event is unchanged by whatever the first one is. And then lastly, what's the probability that the third randomly sampled thing is also blue? Well, again, it's not influenced by the prior two, so again, we can say that that's 1/4 again. Right, so we can say a similar thing exists for green, red, and purple. So it would be a quarter for the first one being green, a quarter for the second one being green, given that the first one is green, and then a quarter for the third one being green, given that the second one is green. And hopefully you can see that the scenario doesn't really change based off what color we're dealing with, right? So this one would also be a quarter, 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 and this one would also be a quarter, and a quarter. So now our total probability is then equal to, well, we just have to add all these up, right? Because we'll either have all blue, or all green, or all red, or all purple, right? Because we want to see the chance that all of the entries are the same, right? So there's never a chance that we could have all blue and all green, right? That doesn't really make sense. So by the addition rule, we can add these events together. So we have 4 of the exact same thing. So we have 4, it's not that great of a 4, 4 times 1/4 times a quarter times a quarter, which just simplifies to 1/16. So what this tells us is, if we randomly sample 3 elements from this array, blue, green, red, and purple, obviously with replacement, then there is a 1 in 16 chance that we will select the same number, or the same color, all 3 times. So an alternative approach to this question would be to say, hey, look, so we're going to sample one color, sample a second color, and sample a third color. So what's the probability, so we'll randomly pick some color for our first sample, right? It could very well be either any of blue, green, red, or purple, right? It's equally distributed. What's the probability that the second color is equal to the first color? Right? So for example, if sample 1 is green, what's the probability that sample 2 is also green? Well, that's just a quarter, right? And similarly for sample 3, given that we have sample 2 is some color that is also equal to what sample 1 is, what is the probability that sample 3 also matches that color? Well, again, that's just a quarter, because there's a 1 in 4 chance that it matches that color. And so here's a little abstract way of thinking of it. What's the probability that the first sample matches what the first sample was? Well, that's just 1. So then our total probability, again, is 1 times the probability that the second sample is equal to the first sample times the probability that the third sample is also equal to the second sample, which once again yields 1/16, which we'd hope that both approaches are valid because they yield the same solution. So either way works just as well in an exam. There's 2 different ways of looking at the same problem. Okay, now for problem number 3. We're given a fill-in-the-blank situation, and we have a word bank up here, and we are left with the task of determining which words fill in the blank. So, important criteria for a statistic to be a good estimate of a population blank include blank bias and low blank. And the blank distribution of a large blank is likely to resemble the blank of the population. Okay, so looking at the first sentence and the word bank that we have, let's try and figure out a word that could fit into our first blank, right? A statistic to be a good estimate of a population approximate, that doesn't really make sense. An important criteria to be a statistic of a good estimate of a population empirical doesn't really make sense. Population doesn't really make sense. Statistic to be a good estimate of a population statistic doesn't really make sense, right? So you can go through and quite quickly cross out a lot of the words that don't really make sense in this context, right? So one of the words that do make sense in this situation is parameter, right? Because in the context of statistics, a parameter refers to the actual value of some sort of variable, right? So a population parameter would be the actual value of the population. So we're talking about important criteria for a statistic to be a good estimate of the number of people in the population, right? So in this case, parameter seems like the best choice. So we're going to go ahead and put a 7 right there. And just for our purposes, we can write parameter there, right? And note that this doesn't disqualify parameter from being used again in a different blank, right? So now next we have something blank bias, right? And then we look back to our definition of bias. What it means for something to be biased is that, bias actually refers to the difference between an estimate of a value and the actual value, right? So if we want something to be a good estimate, we would want the difference between the estimation and the actual value to be quite low, right? Which by definition means we want low bias. And lo and behold, low is one of the keywords we have here. So low bias would make sense in this case. So blank 2 would be 9. So what else would we want to be low when we're talking about a good estimate of a population parameter, right? We have low bias, we need low something else, right? Low control, low probability, low unlikely. A lot of these words don't really make sense. One of the only words that actually makes sense is variability in this case. And that makes sense, right? Because variability is how spread out the data actually is. And if the data isn't as spread out, then the more samples we take of it, the more likely it will look like the actual population parameter. Whereas if the data is the variability is large, then there could be a good chance that we just sample points that are far away from the mean and that are far away from what the population parameter actually looks like, and then that'll tend to give us inaccurate estimates, right? So the term we're looking for is low variability, which would be number 15. So that concludes the first sentence. Now we're looking at the blank distribution of a large blank is likely to resemble the blank of the population, right? So the blank distribution, well, the only types of distributions we know that could come from this list are empirical, right? And we know that an empirical distribution is the distribution of a test statistic as opposed to the real value, correct? Right? So when we run some sort of simulation or a trial, the empirical distribution is the distribution we get from running that sample trial or whatnot, as opposed to the real distribution, right? So we can put empirical down for now. If it doesn't make sense later, you can erase it. But the empirical distribution of a large blank is likely to resemble the blank of the population, right? So going back to the last question, if we have low bias and low variability, then if we take an empirical distribution and we have a large enough sample of items, then that empirical distribution will look a lot like the real population, correct? So now we need a word that kind of fits in to what we're saying. We've been talking about sampling, trials, so random sample actually would fit in here. And then, so if we're talking about the empirical distribution of a large random sample is likely to resemble the blank of the population, well, we're talking about the empirical distribution, so keyword being their distribution, so we want this to resemble the distribution of the population, right? And this sentence makes a lot of sense. The empirical distribution of a large random sample is likely to resemble the distribution of the population, which makes sense. The more items we are sampling from the population, then the more the empirical distribution will look like the actual distribution. Right, so we can go ahead and fill in those blanks. Number 4 would be 2. Random sample is 5. And lastly, distribution is 16. So that's what this fill in the blank question kind of boils down to. Okay, so now it's time for number 4 and our beloved histogram questions. So we have a table called NBA. It has a column labeled salary containing some salaries of 2015 to 2016 players. Right, so you can take a look at the data here. So our first question is, which bin contains more players? 2 to 4 or 4 to 12? Right. So here, it's not the width of the bin that tells you the number of players that we have, nor is it the height of the bin, but rather it's the area of the bin, right? Which is what we're accustomed to with histograms. With histograms, the area of a bin is equal to its proportion with respect to all the data in the data set, right? So let's look at the area first of the 2 to 4 bar, right? So we can say area 1 is about, right? So our width is 2, 4 minus 2, and our height is, let's say, it's less than 12.5. Let's just say it's 11, right? Or something less than 12, so we'll say 11, which is less than 2 times 12, which is equal to 24, right? So we have our first area is a little less than 24. So less than 24% of the data is in that column. Whereas in our second bin, it's much wider, of course, right? So we have 8. And then this bin is clearly greater than the 2.5 mark on the y-axis. So it's approximately equal to, 8 times 4, which is greater than 8 times 3, which is equal to 24. Which means that area 2 is greater than 24, which is greater than area 1, which means that area 2 is greater than area 1, but implying that 4 to 12 contains more players. And that's solely for the reason that the area of the 4 to 12 bin is greater than the area of the 2 to 4 bin, because that's how players are represented in this histogram. Okay, so problem 4b now. So to see more detail in the 4 to 12 range, the histogram will be redrawn with bins as shown below. So we have our new bins here. The display includes the heights that are available from above. So now our question is, if possible, provide a numerical expression for each missing height. So we want to try and figure out, is there some way we can solve for this height 1 and this height 2? And if so, do not simplify the arithmetic, but how could we go about doing that, given these two facts? Right? So let's take a look at number 1 first. So what it says is that 56 of the NBA players, 56 data points are in between this interval, right? 56, right? And we know that in total there are 417 players that we're looking at, right? And we know that since when we're talking about percent per $1 million, we know that 2 minus 0 times 17.63 plus 4 minus 2 times 11.39 plus 6 minus 4 times I plus 12 minus 6 times second I plus 18 minus 12 times 1.6 plus 26 minus 18 times 0.45 is equal to, well, that's 100. 100% of all the players in the NBA. Because we're talking about percent per $1 million. That's 100%, which we know is equal to 1, because all histograms areas must sum to 1. But here we're dealing with percent, so 100 is just fine, right? So what the area of each bin corresponds to is the number of NBA players, or the percentage of NBA players, rather, that fall into that bin. So the area for example, of the 0 to 2 bin is the percentage of players that fall in that bin, right? So the area of the 4 to 6 bin should be the proportion of players that are in that bin, right? Which we're actually given, right? Because we're told that 56 out of the 417 data points actually occur in our region, right? Of course, we would times that by 100%, but we're not quite done yet, right? Because we know that the width times the height, height, is what this is equal to, right? We know the width times the height is equal to the proportion. But we're actually given the width right here, and we're trying to solve for the height, right? So we know the width of this bar is 2, so this implies that the height is equal to 56 times 100 over 417 times 2. And that's, of course, in percent, but this is a representation for the height, or rather, I. So to go over it again, we're told that 56 out of 417 of the NBA players lie in this bin, and we know that the area of a bin is the proportion of NBA players that are in that bin, and we know that the area is 56 over 417. But since we're dealing with percent, we need to multiply by 100%. And we know that's equal to the height, or the value of I, times the width of the bin, which is 6 minus 4 is equal to 2. So then we can divide by the width of the bin and get the height for this one. So now that we have the heights of all bins but one, is it possible to find number 2? And indeed it is, right? Because if we set up this expression for the area that we already have, right, we can say 2 times 17.63 plus 4 times 11.39 plus 2 times 56 times 100, 417 times 2, skipping over this one, plus dot 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 plus whatever, 8 times 0.045. That's the area of everything except for the area of this bin, correct? So that means the area of the second bin should be the total area subtracted away divided by, this will be the area of this bin, of this bar, but the height of that bin should be that divided by the width of this bin, which is 12 minus 6, which is 100 minus A over 6. Right, because we know all the area sums to 100, so 100 minus A will be the proportion or the area of this bar, but since we want the height and not just the proportion, we need to divide by the width, because like we had before, height times width is equal to area. So we need to consider both parameters. So hopefully that makes a little sense. So yes, it is possible to provide numerical explanations for both, expressions for both, and we've done just that. And you wouldn't really need to simplify anything further than what we have here. Like writing in terms of A and then subtracting away from A, like that's just fine in terms of an answer for the exam. So our next problem, number 5, is a little less computation heavy, and it's a little more theory heavy. So we're told that a group is studying the effect of smoking, and the participants were separated into groups according to gender and age, and then each subgroup they came back with the same result, and that was that the people who never smoked were on average more healthy than the current smokers, but the current smokers were on average healthier than the people who had recently stopped smoking. So they're saying in terms of health, non-smokers, rather never smokers, are healthier than current smokers, are healthier than recently quit smokers, whatever, sure. So what this is asking us is, should the current smokers have been advised to not give up smoking? Right? So what they're saying is, what the fallacy here is that, the current smokers are healthier than the smokers that recently quit. So why should they quit smoking if they're going to become less healthy? Right? And this argument clearly doesn't hold up. And one of the reasons for that, actually, is because we could say that the health of the people who just stopped smoking was so bad that they decided to stop smoking, right? So eventually the people who stopped smoking, their health will eventually become greater, right? But since they just stopped smoking, their health quantity, I guess, will be less than the people who are currently smoking, because the people who are currently smoking have not yet had the impact of smoking yet sit in on them, right? Or yet to sink in on them, right? So the people who just stopped smoking, their health was so bad while smoking that they decided to stop and improve their health. So they're recovering, but they're still currently less healthy. But they're on an upward trajectory with respect to the people who currently are smoking. So, of course not. They should have definitely still been advised to give up smoking. And the argument that people who recently quit smoking are less healthy is, and that being a reason to not quit smoking is indeed a fallacy and not true at all. Okay, so now we're on problem number 6, which is a null hypothesis question. We will also have to write a simulation in this problem. So the scenario that we're given is that some sort of clinic is trying to test some new system, and on Mondays, Wednesdays, and Fridays, they test the new system, and on Tuesdays, Thursdays, and Saturdays, they continue to use their old system, and then at the end of some period, they've noticed that 212 requests have been assigned to the new system and 277 to the old system. And like our null hypothesis, or we would assume that we would get around a 50%, or like around a 50-50 split of assignments to the Monday, Wednesday, Friday set and the Tuesday, Thursday, Saturday set because of the same number of days. But one clinician says this method is biased against the people who call on Mondays, Wednesdays, and Fridays. And she's saying that this method is not fair, and if we tossed a fair coin for each request, we wouldn't have ended up with so few requests. And clinician B says, no, the results are just like tossing a fair coin. So our null hypothesis and our alternative hypothesis in this case, and our simulation, will be based off the fact of checking to see whether or not this could occur, given that the assignment of Monday, Wednesday, Friday, and Tuesday, Thursday, Saturday is 50-50, right? So our null hypothesis, what we believe right now, is this method is fair, right? Because that's what we assume right now, because we're assigning them with equal amounts of days, Monday, Wednesday, Friday, Tuesday, Thursday, Saturday, it should be fair, right? And so the alternative hypothesis is what we will believe if our hypothesis test gives us a low enough empirical p-value, right? So we're going to run our simulation, and we're going to run our simulation and find the probability of what actually occurred, of having 212 new requests and 277 old requests. We're going to run a simulation and find the probability of this actually occurring. And so if the probability of that occurring is quite large, then we know that, okay, this definitely could have happened, and it's in a realm of likelihood, so there's nothing to worry about, and this method is still fair. But if our p-value is less than, for example, 0.5, or some other number, which we have, we're not actually calculating the value here, then we have to stop and say, hey, wait, the probability of this occurring was so small, maybe it isn't fair, and let's look more into it, right? So the alternative hypothesis is this method is biased against the Monday, Wednesday, Friday requests. Right, well, this is what clinician A is claiming. Right, so now in part B, we actually have to write some sort of hypothesis test for this to try and find an empirical p-value, which we can use to analyze whether or not this should have actually occurred. Right, so we know that we have 489 entries in array 489, 212 of which are new and 277 of which are old. But that's not the array we actually want to use in this case, right? Because that's already assuming the results to be true. what our null hypothesis is that the method is fair because Monday, Wednesday, and Friday, and Tuesday, Thursday, and Saturday have equal likelihood of being chosen. So we don't want to use this array 489. We want to use the array 2, which is the string new and the string old, and we're going to randomly select from. We're going to randomly select either new or old, which is equivalent to flipping a coin, which is what clinician A claims. This is not equivalent to flipping a coin, right? So essentially what we're going to do is flip a coin 5,000 times and see if it's possible that we have less than 212, less than 212 heads. That's essentially what we're going to do. Find the probability of there being less than 212 heads. Right? So every time, for each of the 5,000 times, we're going to randomly choose something from array 2. And how many times are we going to do that? Well, 489 times, because that's what occurred here. We had 489 requests, 212 were new, 277 were old. We had 489 total. And we're going to count the number of times that this draws list was equal to new. Right? Because draws will be assigned to some array that has 489 elements in it. That'll either be, each of which are either old, or new, right? And so on, right? So that's what draws is. So we want number new is the number of times that the array draws is equal to the value new, right? So it's the number of times we get new. And then now stats will be an array that holds all of the values that we've accumulated so far, right? So stats, np.append stats comma number new, what that does is it'll take our current stats value and add on the newest number new, right? So in our first iteration, stats will go from an empty list to some number, let's say 300. And then our second iteration it'll add on the second value of number new that we randomly generate. So pretend that's 156. And it'll do this 5,000 times, right? So now what we have is at the end we'll have a list that is 5,000 elements long called stats, and it'll have number, and so on, right? And so what we want to find is the probability that these numbers were less than 212, right? So we want to find the count non-zero of stats being less than or equal to 212, right? So we want to find, okay, we ran this thing 5,000 times. How many times did it occur? Or how many times was it the case that there were 212 or less numbers new? Or 212 or less elements being new in arrayed in draws, right? But we have to divide that by 5,000 because sure, here this values are successes. We also need to divide by the number of trials, which will give us our empirical p-value. And so this is the final solution to this part of the problem, or this problem actually. So this simulation and this empirical p-value will tell you, it'll give you a probability for this occurring. And then once we get this value, we can use this to analyze whether or not this assignment system is biased or not. On to number 7, which is a histogram analysis question. So, a fair dice is rolled. If it shows 1 or 6, you have to pay your friend $1, right? So with probability of 1/3, you're going to lose $1, right? If it shows 2 or 5, you're going to gain $1, right? So probability of 1/3, you're going to gain $1. And it shows if it shows a 3 or 4, nobody pays any money, right? So with the probability of 1/3, you're not going to gain or lose any money, right? So now the question is, we ran this thing 10,000 times. Which histogram represents my net winnings? right? In over 60 games. So we pay 60 games, and then we pay 60 games, play 60 games 10,000 times, right? So which histogram represents this data and why, right? Well, so first we know that the probability of being greater than 0 and the probability of being less than 0 and are both equal, and they're also equal to the probability of being at 0, right? So we would assume that our histogram would be centered around the value of 0, right? Our net value would be simulated around 0. Also, if we were to, off to the side, calculate the expected value, a third times -1 plus a third times 1 plus a third times 0, that's around 0. So on average, you'd expect to not gain any money. So it wouldn't make sense for one of these graphs to not be centered around 0, right? So that right there, you can go ahead and take away the third histogram, right? So now we need to talk about one way we can narrow down the graphs is look at the axes on here, right? So here, histogram 1, we have 60 and -60, and the bars are just as high with -60 and 60 as they are around 0, right? So now, is the probability of that occurring actually justifiable, right? So what's the probability of actually winning 60 times, or winning $60, right? It would be 1/3 the probability of winning $1 times the probability of winning $1 again. The probability win 60 times the probability of winning another $1, and so on, which actually becomes the probability of winning $1 once to the exponent 60, which is so small, very, very close to 0, which is nowhere near 0.8, right? So these values should be nowhere close to the probability of winning 0 or $1, right? Those values should be great. But the values are the heights of the bars representing the probabilities of winning $60 or losing $60 should be very, very small, because this probability is so small, right? So right away we can take this graph away, because the end probabilities need to be much less than the central probabilities, right? Because, for example, probability of winning $2 is equal to a third times a third, which would be a ninth, which already isn't too great, but it's much closer to the probability of winning $1 or $0 than the probability of winning $60. So that this graph is uniformly distributed. We don't really want that. And by the same token, this one is also not uniformly distributed. This one is uniformly distributed, but also the axes on this one don't really make sense, right? Because we want to simulate the net winnings of $0 or $1 or $2, right? Here, having n bins of 1.5 and -1.5 don't really make sense in terms of this graph, right? Because we play this game 60 times, right? So there's no way that the greatest bar you have is winning 1.5 games, because we're doing this 60 times. So this graph also does not make any sense. And so we're left with histogram 2, which indeed is the histogram that would represent this, for a number of reasons, right? So first of all, it's centered around 0, because the probability, the expected value is about 0, and the further you deviate from 0, the lower the probability of that occurring is, right? Which is what we'd expect for this sort of game, right? So the probability of winning about $1, losing about $1 is about the same. The probability of gaining $2, losing $2 is about the same. So it's also symmetric, and as you can see, winning more than $20 or losing more than $20 is almost impossible by this graph, right? As you can see, 1/3 to the exponent 60 is so small, right? 1/3 to the exponent 20 is already very small, and which is what we represent here. So we'd assume it to be normally distributed, and so this histogram 2 would be the histogram that would represent this situation. And I just went over some things that you could say as an explanation for that, and hopefully it's clear at this point. Okay, and our last question is one dealing with the total variation distance, and we also have some Python manipulation to do. So what we have, we're given a table called voters, and in it it contains rows which contain data about voters for some large national sample. So each row will contain a state and a choice, right? So each row will look something like CA candidate A. And then maybe like Alaska, that's Alabama, isn't it? I'm not American. Candidate B. And then maybe another California, candidate B, right? So right now, it's not that an entire country or an entire state is voting for one candidate. They're just saying, okay, here's a voter, they're from California, they voted for candidate A. Here's a voter, they're from California, they voted for candidate B. Right? So these are not already grouped. Okay? So that's an important distinction to make. Right? So now, we want to find the total variation distance, which we'll get to in a little bit. But the beauty of this question is you don't really need to already know the process of doing this because they kind of walk you through it. Right? So the first step we want is we need to create a table of the data of all California voters containing just one column, choice. Right? So you know how before we had California, Alaska, then we'll have all the other states as well, votes from all the other states. What we want is just only the votes from people who are in California. Right? So this is a pretty simple where statement. We want just voters where their state is r dot equal underscore 2, good old California, because we're just using the 2-letter code, right? But not only this will just give us a table that says CA, like candidate A, okay, CA undecided, CA, okay, that's pretty terrible handwriting, but you get it, right? Like it'll say California every time. But our array is called California voters, right? So we don't need each row to tell us that it's in California, right? So what we want to do is just select the column choice, as the question tells us right here. So now all we have is a one column or table. The title heading, the column name is choice, and then it'll say like candidate A, candidate B, undecided, candidate B, candidate A, and however many there are, right? But see, now the annoying thing is there'll be multiple candidate A's, there'll be multiple candidate B's, there'll be multiple undecideds, right? So what we would like is to have a simple way to just look at the total number of votes that each candidate got, right? So what we want is something like choice and count, right? So we could have cand A, cand B, undecided, and we can say, like, I don't know, 1, 0, 2, 3, 5, 5, 3, 2, and like 15 or something. I don't know, right? We just want a way to be able to say that, okay, here in California, this many people voted for candidate A, this many people voted for candidate B, this many people were undecided, right? So here, we need to group by the choice, right? Because this is exactly what group does. It goes into every row and says, okay, it belongs to this category. It has this same name, choice. This has the same choice. This is the same choice. Let's find out how many rows have the same choice value. How many rows have the same choice value? Candidate A, candidate B, and undecided, right? So it's a typical group question. Group by the choice. And here they say that they want an array, right? So that this is going to give us this line on its own will give us this array, this table, right? We want an array. So instead of we don't really want the names candidate A, candidate B, and undecided, because we know the array is only going to be of length 3, and that the 0th element will refer to candidate A, the first element will refer to candidate B, and the second element will refer to undecided, right? So we can just do dot column count, and now we're reduced to just an array: 1, 0, 2, 3, 5, 5, 3, 2, and 15, for example, right? But we want in proportions, right? So we don't want the raw number of people who voted for each of the candidates. We want the percentage of people in California that voted for each of these people. So what we want to do is divide this by CA underscore voters dot num rows. So this is essentially, instead of setting our values to 10, 23, 55, 32, and 15, it's setting them equal to 1023 over 1023 plus 5532 plus 15, and then 5532 over the same sum. And again, these numbers are just made up. 15 over 1023, 5532 plus 15. So now it won't give us the raw number of people who voted for a certain candidate A, B, and undecided. It'll just tell us the percentage of the population of the state, which is what the question wanted. Right? And so now our last line is, okay, assume we've done the same thing for Florida. Like, we don't actually have to go and do it. But assume that we have our California distance array. We also have some Florida distance array. Find the total variation distance. Right? So now, the definition of total variation distance, if you don't remember, is, so for example, say we have CA dist is equal to, I don't know, C1, C2, and C3. And say FL dist equal to F1, F2, and F3, right? Where C1 would be the percentage of people who voted in California who voted for candidate A, C2 would be the percentage of people in California who voted for candidate B, and C3 would be the percentage of people in California who are undecided, and then F1, F2, and F3 similarly would be those same values for Florida, right? So the definition of a total variation distance is, okay, you go through and sum together all the absolute values of matching pairs, right? So our TVD, and this is for any data set, not just CA distance and Florida distance. You go through and you subtract the first element of each one, take the absolute value of that. You find the absolute value of the second two, of the third two, right? And if we had more than 3, we would do this for as many, however many as we have, right? So we're summing together the absolute value of the difference between each of these. And then we're going to divide that by 2. Right? So TVD will be set equal to the sum of the absolute values of the differences between corresponding elements of the array divided by 2. And that's just the definition of total variation distance, and that's something you should have learned in lecture. So now we need to try and figure out how to apply that in terms of our Python commands, right? So we know at the very front we can pull out a 0.5 times, right? And then here we have a couple pluses, so it looks like we're going to be doing some sort of sum. So we can go in and add an np.sum. And then what exactly are we summing, right? We're summing the absolute value of certain distances, right? So we want to sum the np.absolute value of FL dist minus CA dist. Right? And if you recall, in Python and NumPy, if you just subtract 2 arrays, it automatically subtracts elements at each spot, right? So this will automatically be reduced to F1 minus C1, comma, F2 minus C2, comma, F3 minus C3, right? So that's what this will be equal to. So we just need to take the absolute value of every element in this array, sum together all of those elements, and divide by 2. And that's the definition of total variation distance. So then, here, we're left with our final answer, and that's the TVD. And that just about concludes the Fall 2016 Data Science 8 midterm walkthrough video. And if you have any questions, the course Piazza would probably be the best place to start. And that's it.